Share my screen. Okay, let me start playing. All right. Okay. So it's a kind of a special way to record. So hi everyone. I'm Jiaqi Cai, a condensed matter experimentalist in MIT physics as a Pappalardo Fellow this year. So I'm going to talk about electron choreography or electron dance in Flatland. Basically, as the title page shows, I will talk about two-dimensional material, how we engineer and uh, play this electron dance and create exotic quasiparticle or anion in this two-dimensional material. I will talk about the history. Of course, myself is involved in from Hall effect to zero field anions. All right, so let's start with actually the source of my inspiration is a book by Edwin. So in his book, this Flatland, talk about this romance of many dimensions. So he basically focused on this two-dimensional world. Okay, so there is an object or the main character is actually this square. Okay, so square claim that he know better than this what the point. Okay, in the one-dimensional world, living in the one-dimensional world. So this means the square is actually claim that he know better than point in for this one-dimensional because he live in a higher dimension. And he measured the three-dimensional creature and say that, oh, I cannot actually even understand this three-dimensional world. So is there actually a hierarchy of higher dimensional to low dimensional? It's actually not true. So actually, in our real world, physics told us that on the contrary to this book, in some sense, as a three-dimensional creature, we know less in this two-dimensional world. And I'm showing you this a beautiful graphene image that actually the electron living in this two-dimensional graphene shows those exotic behavior that is hard for us to understand. Right. So this so-called hard to understand effect is a fractional quantum anomalous effect we'll talk about today. So in my thesis work, my PhD thesis work, we complete the last piece of this Hall effect family happening in two-dimensional world, starting from 1879 Hall effect to the final destination of fractional quantum Hall effect. So in this almost 1.5 century, what is happening? So why people are so deep into this two-dimensional world, this two-dimensional flatland, and what's new physics we have been discovering. So to be very short, the discovery in my thesis work, the fractional quantum anomalous Hall effect, facilitates anion, a fractionalized quasi-particle, into practical research. Basically meaning now today we can quite easily study them, quite easily engineer them, and in the future maybe we can use them. Maybe we can use them to build some even more exotic faces that we would like to see. So my program at MIT is actually trying to use those quite standard, three-dimensional wave, say a photon wave, a light wave, or a spin wave to create, control, or braid this two-dimensional anion, which I will explain later, and finally measure them in this platform of a fractional quantum anomalous Hall effect. So now you will be very interesting. Okay, what is actually fractional quantum anomalous Hall effect? So I will explain to you soon what is every word from a Hall effect to this fractionalized one. So begin with Hall effect. So it was discovered in 1879 by Edwin Hall in this funny, gold leaf, maybe the first carrier of two-dimensional electrons. All right. So what he did is he played a outer plane magnetic field, and you can see, as you know from college physics, that positively charged and negatively charged objects but moving in opposite direction. Okay. So when you measure the resistance, it's basically charge accumulation on the side wall. You'll find that for electron in semiconductor, the whole resistance will be negative. Okay. It's a negative slope as a function of increasing magnetic field. But for holes in the semiconductor, it will show you a positive slope as a function of magnetic field. So in some sense, Hall effect tells that the concept of hole is essential for our understanding of this semiconductor behavior. So then 100 years later, actually, Klaus van Cleansing, after, in this 100 year, a lot of things happened, bad or good, world wars, and, this new technology, including semiconductors, superconductors, and low temperature techniques, which actually facilitated the discovery of this quantum Hall effect. In low magnetic field, you can see the electron still behave like an electron, okay? So it's linear Hall effect. However, in high magnetic field, the whole resistance start to find some obstacle, okay? It forms this discrete plateau, okay? That is very, very flat, okay? So how flat it is, actually physicists has measured. The whole resistance is actually an integer fraction of fundamental constant, okay, number, right? So the fundamental constant is Planck constant for H and electron charge, E. So what's the exact number of them after some calculation? It's actually integer fraction of 25.8 kilo ohm. All right. So you can measure this fundamental resistance in a lot of different material. For example, graphene, zinc oxide, gallium arsenide. You can measure it in different places, say in Greenwich, in Boulder. You can also imagine one day you can measure in Moon, on Mars, or even close to a black hole. But you always find this fundamental quantized Hall resistance, 25.8 around 25.8 kilo ohm. So it's I would claim that it's actually a very good choice for first contact with aliens, because aliens may be, for example, they may measure it on Mars and they arrive at the same number as us. All right, so we understand quantum Hall effect very well. At a very high magnetic field, the electron is not like this individual trajectory, but they follow this cyclotron orbital. Okay, they start to localize on the bulk. However, on the edge, the electron will behave like this skipping orbital. Okay, so now if you measure the whole resistance, it's actually the integer nature of electron. You can measure 1 electron, 2 electron, 3 electron. That leads to the integer number of edge state. Then it's actually measure the quantum nature of this electron on the edge. You have 1 electron, 2 electron, this quantized nature. So in a funny way to understand it is that in linear Hall effect, you have this guy like a moving sidewall. However, in this quantum Hall effect, you have this quantized orbital for them. Right. So what is a fractional quantum Hall effect? So fractional quantum Hall effect is actually discovered right after quantum Hall effect, after they obtain this higher quality sample as well as this higher magnetic field. So what they observe is that there are much more fraction than this integer quantum Hall effect. So the main takeaway is that now this quantized Hall conductance is not just the integer filling, but also this fractional filling. All right, so if we say before that integer number of this edge state is the quantum nature of this electron on the edge, this fractional number of edge states really happen in this fractional quantum Hall effect? The answer is maybe yes. So thanks to the pioneer work by Frank Wilczek, he actually proposed that the possibility of anion or that carries this fractionalized quantum number. So for anion, that is a two-dimensional topological object that is very different from our three-dimensional world. So in three-dimensional world, we only have this boson, fermion that consists of our material world. However, in two dimension, you have this actual anions that is that when you exchange these two anions, they will pick up an arbitrary phase, or they will not even look like themselves after you exchange to anion. That's the special property of anion. You can also visualize it as one electron can fractionalize into this fractionally charged quasiparticle in fractional quantum Hall effect. So this has been proved by Robert Laughlin, which is another MIT alumni. He proved that the anion is actually responsible for this fractional quantum Hall effect. So he write down and the exact solution of the physical modeling of the problem. But unluckily, even though we still do not understand the essential ingredients to required to create this anion by us. Right. So why people are so deep into this anion physics in Flatland? because it's useful. It's fundamentally interesting. It's different from fermion and boson, but it's also very useful. It's actually a dream place for quantum computation. So the thing is actually, I just described before that the fundamental definition of anyon is that when you exchange them, there was some interesting effect happening on the quantum wave function of this anyon object. You can use them to braid in space-time and form this very interesting carrier for quantum information. Right. So this is kind of inspired by interesting talk in the 16th Symposium that ancient people actually use this so-called Cupid node in this ancient computing machine that you can have these nodes on a rod and then you use them to store information and performing computation. So this quantum computation essentially is that you can initialize or create anyon and then apply those so-called quantum gates or computation by braid them, by moving them around. And then you can output or by measuring this anyon wave function. So that's the essential point of the so-called topological quantum computation based on anyon. All right, so let me give you a very quick summary about what has been discovered before 1982. We have the Hall effect, quantized level of it with this integer edge state, and the fractional quantum Hall effect that hosts anyon. So in short, is that in quantum Hall effect, this electron has this cyclotron orbital, but in fractional quantum Hall effect, we have essentially new quasiparticle called anyon emerge into this platform. All right, so now last word, anomalous. So why we mean fractional quantum anomalous Hall effect is important, and why it took us almost 40 years to arrive there. So this is the exciting part. So Edwin Hall actually discovered this anomalous Hall effect 3 years almost right after his discovery of ordinary Hall effect. So the essential point that is different from linear Hall effect or ordinary Hall effect is that now Edwin Hall measures a magnet. Okay, so the electrons spin are polarized on its own. Right. So now there's no need of magnetic field because the spin of the electron form a magnet. Right. So now he discovered even at zero external magnetic field, it can still present this Hall effect called anomalous Hall effect. So an interesting metaphor about this phenomena is that for Hall effect, you want to control the movement of electron or holes. You have to have a conductor or a DJ for them to play with, right? So anomalous Hall effect is kind of this electron are moving without any external conductor or DJ to play music, to control them. Okay. So this kind of self-organized motion of these happy electrons. So what is we also have the quantized anomalous quantum version of it, so-called quantum anomalous Hall effect. That is discovered much after the anomalous Hall effect. So there's a lot expositionary, discovery of topological material that boost this discovery of quantum anomalous Hall effect, where you can observe the quantized plateau even at the zero magnetic field. Okay, this magnetic field is just for convenient to visualize. Okay, it's really, really quantized. All right. So now the story is almost complete. There's only one last pieces that is left there. It's the fractional quantum anomalous Hall effect. So that's finally our main character in this Flatland, just like the square in the book of Flatland is this fractional quantum anomalous Hall effect discovered 2 years ago in my PhD thesis work. So what is the essential of this fractional quantum anomalous Hall effect? Why it took us 150 years after the Hall effect? We should have observed it right after the Hall effect, right? Because it's quite a lot of new concepts, including the development of fractionalization concept, like new quasiparticle can emerge from this electron in 2 dimensions. And the magnetism, we need to know how to control magnetism and topology. All right, so that sounds like a mission impossible. You want to control a material that contains a million of these denser, quantum denser, without any conductor. You cannot use any magnetic field to control them. So you lose almost the most powerful tool that condensed matrix experimentalists have. How are you going to achieve it? Thanks to a very close collaboration, so-called Moiré, engineering of MIT Building 13 and 6, from say Raymond Ashuri of the Hofstadter butterfly physics to Pablo, he's holding his hand. There's a beautiful Moiré pattern, and the theoretical study by Liang Fu and Sensao, among many others. We develop a solution finally, is that you have to train the electron by so-called Moiré engineering. So Moiré engineering is basically you place these two Flatlands together and have a slight angle mismatch. This creates, in our three-dimensional eye, we can see it. It creates a landscape, a potential landscape for electrons. Okay, so electron can feel this potential within this lattice. Okay, you can see this valley and hole, and then the electron, we can program the motion of the electron by this Moiré potential that provide an equivalent role as magnetic field. Now we can play with them, or we can create this potential landscape just by Moiré effect. So that leads to the discovery. That is one essential point to the discovery of a fractional quantum alarms Hall effect in my PhD group, led by PI Xiaodong Xu. So here's me. You can see I'm staring at this device. How we can make better devices is the essential of observing this novel quantum effect. And we are very happy when we are taking this measurement finally in the first time see the signature of a fractional quantum alarm Hall effect. So what's the essential observation? It's like in the zero magnetic field, you sweep, you control how many electrons in the material, and you see multiple fractionalization phenomena. Like in these two quantum Hall plateau, an electron can be fractionalized into three anyons, like this anion, then contribute to this fractional quantized anomalous Hall effect. We also observe other type of fractionalization, like the electron can band with two flux contributed by the internal motion of electron itself to form this so-called composite fermion states. All right, so why is it important? Why we want this, physicists want so much this zero field fractional quantum alarms Hall effect, because it facilitates any research with diverse method. You are now not limited by magnetic field. Superconductor doesn't like a magnetic field. You don't need any magnetic field. You can go to higher temperature. That's why people are starting like internationally about this effect and using very diverse method. Say in Santa Barbara, people use superconducting sensor to sense the local magnetization. It's done by one of our old friends, Andrea Yang, who is a Pappalardo Fellow before. Also, people are trying using superconductor to inject into these devices to study how superconductor interacts with this fractional quantum alarms Hall effect. This is also by another of our old friend, Sanfeng, who is another Pappalardo Fellow. People also see, amazingly, this zero field anion in all carbon material at MIT, actually, by one of our very nice MIT faculty, Long. We discovered this fractional quantum alarms Hall effect in pentalayer from hydrographene. Actually, few months right after our initial discovery of this phenomena. And also people can use the very local probe to looking at locally what's the anion look like by this so-called microwave impedance microscopy measurement led by Stanford scientist Jiaqi Shen. And amazingly, the leader of that paper is will also join MIT soon as incoming MIT faculty, Judy. All right, so we have all of this exciting progress led by MIT. It's already becoming a leading center of studying this fractional quantum alarms Hall effect. So what I'm doing at MIT, so my experiments in MIT essentially involves using this three-dimensional prop. So we are living in three dimensions, so we can only use three-dimensional tools. We use the three-dimensional tools such as the spin wave. The spin is a three-dimensional thing that scatter into the device, trying to create and operate or braid this anion of quasiparticle, and finally detect them, the property of them, or using say a photon as the prop. So that's essentially the experiment that is going on at MIT using this fractional quantum alarms Hall platform as a platform to actually study in detail what's going on with this anion. And finally, maybe we can solve the puzzle. What is actually essential for this fractionalization to emerge? So, the key weapon we have, the key tool we have as a condensed matter experimentalist today is actually have the ability to assemble different flatlands together to get this. It's like a Lego toy to assemble them together, get a very nice device. So we develop a new interesting technique here at MIT, actually just the building a few blocks away, called MIT Nano. We use a tip, a local tip, to interestingly make the device very, very clean. So we use a tip to scan across the sample, and you can see as we stack those two-dimensional flatland together, they don't like each other, right? So they will trap some bubble, some impurity in between this flatland, and we find a way to actually remove this bubble just by a tip and scan together and push out all the dust, and you got a beautiful, pristine surface for us to explore. All right, so if you zoom in the central area that you made clean, you will see there's a very beautiful periodic potential generated by this flatland. That's the Moiré potential. And you can imagine that if now you have electron injecting into this Moiré landscape, you have a happy Fermi, happy electron that live within the landscape. All right, so that's the ongoing experiment at MIT. So finally, I want to acknowledge this maybe the most important slide. I want to acknowledge my PhD advisor, Xiaodong. Lots of the work, the concept of fractional quantum anomalous Hall effect is developed right there. I also want to thank my PI at MIT. We develop a lot of new technique as well as a device in-house to explore this anion physics with Pablo and his graduate student, Ray Hao and Xue, two very talented, brilliant graduate students. Of course, in this very I would say, very difficult time for science. Neil and Jen's generosity really matters a lot for us. Okay, I will conclude here, and thank you for your attention and watching this video.